Hello. So in this video, we're going to investigate the different integrals for different powers of sec theta. Okay. We'll of course start with the simplest one, sec squared, and the reason is that according to the fundamental theorem of calculus, if you can find a function whose derivative is your integrand, then the integral of that integrand is equal to that function. So in this case, that is tan theta. Okay, so tan theta, we know that its derivative is sec squared. So trivially, the integral of sec squared theta d theta is equal to tan theta. Okay, plus c, of course. And so that's a simpler one. It's even simpler than your sec theta, which is what we're going to do next. Okay, so the integral of sec theta d theta. So how do we do that? So one trick that we can do here. So of course you can like write this one as like 1 over cos, and then you write it in terms of sine and so on, but it's harder. What you want to do is you can multiply this by the term sec theta plus tan theta over sec theta plus tan theta. Okay, of course you're multiplying it by 1, you're not doing anything, but what it does is you're able to write now your expression, your original is integral, as sec squared theta plus sec theta tan theta all over sec theta plus tan theta d theta. Okay? And what that allows you to do is it allows you to evaluate it by substitution. You let u be equal to sec theta plus tan theta. Of course, du will be equal to the derivative of secant is of course sec theta tan theta. And of course, the derivative of tan theta, like we mentioned, is sec squared theta. And you can see this entire, of course, you have d theta there. You can see this entire d right here is in fact the numerator right here, including the d theta. So that is very nice. And so what you can do now is the original integral of sec theta d theta in terms of u, you can now write that as the integral of du over u, right? Which is a trivial integral. That's just ln u. And of course, you just substitute back the value of u, which is sec theta plus tan theta. And of course, don't forget your plus c, and you're done for its indefinite integral. Okay, so what we're doing here is indefinite integral, not definite. So we don't have any limits. Okay, so we now have sec, we now have sec squared. Of course, the next case is the integral of sec cube theta d theta. Okay, and for this one, what we can do is we can separate the power into two parts. One is the power of 1 sec, and the other one is squared. Okay, and the nice thing about this is that these two functions right here, after we divided them, one of them is actually easier to integrate, which is sec squared, and one of them is easy to take the derivative of, which is sec. So that allows us to use integration by parts. Okay, we let u be the function that is easy to take the derivative, that's secant, whose derivative is of course sec theta tan theta d theta, and the remaining function is of course your dv, which is your sec squared theta d theta. That implies that your v, which is just the integral of that, is tan theta. Okay, so now what happens is when we use the integration by parts, you have uv, so you have sec theta tan theta minus the integral of v du. So v is tan theta, du is sec theta tan theta d theta. Okay, that is your v du. Of course, that will give you tan squared right there when you combine the two tangents inside the integrand, tan squared theta d theta. And what we can do is we can write our tan squared in terms of sec, okay, because tan squared is equal to sec squared minus 1, so that is equal to sec theta tan theta minus the integral of sec theta times sec squared theta minus 1. That's basically your tan squared d theta. And afterwards, we can distribute sec theta tan theta minus the integral of sec cube theta d theta plus the integral of sec theta d theta. And you say, wait a minute, isn't sec cube theta d theta, that's what we're trying to evaluate? And of course, you're right, okay? The left-hand side is of course, our sec cube theta d theta, right? That's it. That is our left-hand side. So therefore, this one on the right-hand side, we can put it on the left-hand side. That gives us 2 integral of sec cube theta d theta. That will be equivalent to sec theta tan theta plus the integral of sec theta d theta. But of course, we know that, we evaluated that, and we said that that was the ln of sec theta plus tan theta, right? And are we done? Of course, we're not yet done, because on the on the left hand side, it's not yet the integral of sec cube. So what you do is you divide all sides by 2. So that gives you the integral of sec cube theta d theta is equal to 1/2 sec theta tan theta plus 1/2 ln of sec theta plus tan theta. And of course, if you're done, don't forget your plus c for your indefinite integral. Okay? So next, so of course, obviously, after sec cube, let's do sec to the 4th. Okay? So the integral of sec to the 4th d theta, we do the same thing. We divide the terms, the powers to the 4th into 2 parts, and this time we divide it as sec squared theta times sec squared theta d theta. Okay, we just divided it into 2, and what we're gonna do now is we write one of them, one of the sec squared, in terms of tan. Okay, so tan squared theta plus 1 d theta, and of course, after doing that, we can what do you call this? We can distribute. Okay, sec squared theta tan squared theta d theta plus the integral of sec squared theta d theta. Of course, the second term here, this one, that's just tan, right? The integral of sec squared is just tan. So now, in order to evaluate this first integral, let's evaluate it using substitution. We let a variable u be equal to tan theta, and what that allows us to do is, if you get that the derivative of that du, that is equal to sec squared theta d theta, which is exactly right here in our integrand. Okay, so therefore the first term in terms of u now becomes the integral of u squared du. Okay, and of course the second term, like we said, is just tan theta. So if you integrate u squared, okay, if you integrate u squared, that's trivial. That's just 1/3 u cubed plus tan theta, and of course we substitute back the value for u, which of course is tan. So that's just 1/3 tan cubed plus tangent. Okay, that is just your integral of sec to the 4th. Okay, theta d theta. Let me increase the thickness of my yeah, we're in fine. Let me make it medium so that, yeah, it doesn't write very well if the thickness is small. Okay, but basically we did now sec squared, sec cube, and then sec to the 4th, all indefinite integrals. What if we're interested to the general form, right? So what if you want to evaluate the integral of sec to the n theta in general? Okay, like, so that you don't have to like repeat them over and over again. Okay, so what we can do is, I would like to do this, and I'm gonna do this by using integration by parts. And when you do integration by parts, you know that the sec squared part of it you can integrate right away. Okay, so therefore, let's divide this sec to the n into 2 parts. One is sec to the n minus 2 theta theta, and then the other one is sec squared theta. Okay, so basically we separated the sec squared from sec to the n. Okay, and now we use integration by parts. So we let u be equal to sec to the n minus 2 theta which of course if you take the derivative will give you n minus 2 sec of n minus 3 theta. And of course, chain rule, you also need to take the derivative of the function inside, which is sec, whose derivative is sec theta tan theta. Okay? And of course, our v will just be dv, rather, will just be sec squared theta d theta, and our v will be tan theta. Okay? Okay? Good so far? So now, the entire integral will become, according to the chain rule, so let's call this entire integral I to the n. So it means, when we say I to the n, the indefinite integral of sec raised to the power n. Okay, that's what we're gonna call it. So integration by parts, uv. So that is sec n minus 2 theta tan theta minus the integral of v du. So v is tan theta du. So this sec n to the minus 3 and this sec I will combine. That will give you sec n to the minus 2. Okay, so you have n minus 2 secant n to the minus 2 theta, and then you have another tan theta there, tan theta d theta. All right. Okay, good so far. So now let's simplify it some more. So that gives you sec to the n minus 2 theta tangent of theta minus, so let me take out this constant n minus 2, the integral of sec to the n minus 2 theta tan squared theta d theta. Okay? And what do we do next? So what I'll do next is, I'm gonna write now your tan squared in terms of secant again. Okay? So this will give us sec n minus 2 theta tan theta minus n minus 2 integral of sec n minus 2 theta multiplied by, so tan squared, you write it in terms of secant, sec squared theta minus 1 d theta. Okay, so that should give you, when you simplify, sec theta, sec n minus 2 theta tan theta minus n minus 2 the integral. So now I'll distribute this. So of course the first term will give you sec to the n theta. The second term will give you, so this is d theta. The second term will give you minus the integral of sec n minus 2 d theta. Okay? So again, this entire thing we called it in. So let's write it down. Sec to the n minus 2 theta tan theta minus n minus 2 quantity. Note that the first term here is just in, correct? This is in, the integral of sec to the n. This second term we can call this as I of n minus 2. Okay, the integral of sec to the n minus 2. Of course, you have a theta there. All right? So now what happens? So now you have n minus 2 I to the n here. We can put this term on the left-hand side. Okay, so that now the left-hand side will give us n minus 2 I to the n, because that's negative, it will become positive on the other side, plus in. That's equivalent to sec n minus 2 theta tan theta plus, so n minus 2, you multiply it with I to the n minus 1, so n minus 2 I n minus 1. Okay, so that is your, that's the simplification. Of course, the left-hand side, this will give you n minus 1, because when you factor I to the n, that will give you n minus 2 plus 1. Okay, so I to the n is equal to sec n minus 2 theta tan theta plus n minus 2 I n minus 2. So what does that mean? So let's simplify. In is equal to 1 over n minus 1 sec to the n minus 2 theta tan theta plus n minus 2 over n minus 1 I n minus 2. Okay? So in other words, we've written the integral of the n powers of secant in terms of the lower powers. And of course, since we know the lower powers of the secant, that's why we were evaluating sec squared, sec cubed, sec to the fourth, and so on, then you should be able to evaluate any sec to the n, okay? And this is called a recursive relation. So the successive, the future values of n, the future integrals of sec to the n will depend on their former values. So now if you write the original function instead of I to the n, if we write it as sec to the n theta d theta, that is equal to 1 over n minus 1 of sec n minus 2 theta tan theta, okay, and then plus n minus 2 over n minus 1 of the integral of sec to the n minus 2 theta d theta, okay? And so that is now the general form for the n powers of, if you want to integrate, you obtain the indefinite integral of the n powers of sec. Of course, you want to put plus c there, okay, so that you won't forget, okay? But if you want to check, for example, is that really right? Let me, what is sec of 2 the 2, n is 2, theta d theta. We know this before, we know this to be equal to tan theta. Well, when n is equal to 2, this will be 1 over 2 minus 1, so that's just 1. Sec to the 2 minus 2, that's just 0, so that's just tan theta. What about the second term? Well, you have there 2 minus 2, so the second term is 0, okay? So it checks out, okay, for n equals 2, all right? So in other words, okay, what does that mean? In other words, if you want, you can check it for like n equals 3, n equals 4, it should work. So the moment you have the lower powers of the indefinite integral of the sec, so sec to the 1, sec to the 2, and so on, then you can integrate the higher powers all day long, okay? So that's it. So this is our general result. Let me box it with a blue ink right here. So this one is the integral of sec to the n in terms of the integral of the lower powers of secant, all right? So I hope you learned something today, and thank you for watching, and I'll see you in the next video. Bye-bye.